Alrighty. So my name is Reid Mello. I'm on the Globus Compute team. Been with Globus for just under a year. Worked on a number of different features within the compute platform, but today we'll talk about the executor, which is really the process of submitting tasks to remote endpoints. All right, so first thing to cover is the executor class. Again, as I mentioned, it's part of the Compute SDK. There's other ways to submit tasks, but this is the preferred approach to basically submitting tasks and then automatically collect the results. And here we're importing the executor class from the SDK. Important thing to point out is that we've tried to keep as much parity between the standard like Python executor class. So if you're familiar with thread pool or process pool executors, works very similarly. So like, for example, here, the kind of standard route would be using this as a context manager. The .submit call, you pass in the function, your args and your klargs, you return a future, and then we'll automatically wait for results and populate the future. We'll just quickly cover the compute future class. It's like essentially just it's basically just a Python future. There's a small difference, which I'll get into in a second. So same things you'd expect. .result is a blocking call that will wait for results. In our case, we're waiting for upstream services. .done or canceled or a number of other the non-blocking calls are all the same. In this case, you'll receive a Boolean immediately indicating whether the result is ready. So you might ask, what's the difference? It's really just that our futures are tied with task IDs. And so it's literally just a subclass with basically, I believe that's all we're adding is just a single attribute for task ID. It's valid to create a compute future without a task ID, but there's really kind of no purpose. So we technically do in our workflow, which I'll cover in a second, but as soon as we can, we associate a task ID, and then you're kind of prepped to then wait for results. All right, so this is a quick peek under the hood of kind of what's going on. This is obviously not an exhaustive diagram of the compute architecture, but it kind of has all the important pieces to understand the flow here. So on the left, we have the compute executor. Again, this is the SDK, right? So this is your laptop or script, wherever you're running the executor. On the right, you have an endpoint. So a compute facility in the cloud could be on the same laptop you're using. The flow will be the same here. So first step, we submit our task. So this is, you can think of this as analogous to a single submit call. Technically under the hood, we have an event loop and we're queuing tasks and we're batching them together, but for all intents and purposes, this is this like single submit call in which we serialize the function in arguments and we send to the web service. The web service then responds with a task group ID. So it's the group of tasks, but more importantly, the individual task IDs. And at this point, although you receive a future immediately, we can now associate your future with the appropriate task ID. So now the future is basically prepped to wait for results. So the web service will do a bunch of things. Yeah. So a bunch happens at the web service here, but the important part for this talk is that we then enqueue the tasks to an endpoint specific task queue. That task queue is created when the compute endpoint is registered. So we created endpoint specific task queue, and the compute endpoint is now a consumer for that RabbitMQ queue. I said it's a consumer, so it's going to pull down your tasks. You serialize the function and the arguments, run your compute. We then get a result. We then serialize the result, and we publish that to our, in this case, task group specific results queue. There's kind of a lot that I'm glossing over in this part right here. We technically have a result processor, and we're doing some cube, routing and whatnot. But for all intents and purposes, this is the important part: is that we're publishing to some task group specific results queue. So we make our way back to the executor because when we actually submit a task group, we instantiate an object we call the result watcher, which again does a few different things, but the main point is that it's a consumer of the task group results queue. So yeah, we're just waiting for our results. We pull those back down, and we will deserialize and then associate with the appropriate future. So at this point, we have the task ID and the associated result, and we can populate your future. So now you're just calling .result. All right, so I'll go through a quick example workflow. So you'll create some functions, func1, func2, whatever is populated in there. So let's say, for example, I want to submit some tasks to an endpoint running on Polaris at ALCF. So this is just an example. I'm just going to submit 100 tasks that will call function 1, and I'm going to use the iterator items as arguments here. So now I'll have a list of 100 futures that are waiting for results that will return in no specific order. And then let's say I want to then submit tasks to an endpoint running on Midway, which is in UChicago, but I want to use the former results as arguments in the new task. So it's kind of a silly example here. So the main thing to call out here is that because we keep lots of parity between the standard Python executor in the standard Python library and the Python future, we can use things like as completed, which is in the concurrent futures package. And so for anyone who's not familiar with this, this is basically, so it's going to return an iterator of futures that are ready essentially to do something with, to work with. And so I can pass now in the Polaris futures, none of which might be ready yet, but as they become ready, I can now immediately send my, enqueue my, or submit my new function that's going to call function 2, or my new task that will call function 2, using the result from the previous calls to Polaris. Yep. All right, that was it. Any questions? Woo. Christine?
Yeah, so I mean, in that example workflow, you could also do that in Globus flows. Like, what's the advantage to doing it the way you've presented it versus like no different?
Well, the difference is if that's literally all you're doing, then you might probably just want to write a simple little script. Yeah. So yeah, I mean that I'm just really that example is just to illustrate that we're keeping lots of parity with objects in the standard Python library so that you can leverage things like that. But yeah, no, I mean our company line would be like, we use Globus flows. I mean, this is complex work. I mean, Josh would probably quibble with that. I mean, in that specific example, no, I would say not. But if you're building like a complex workflow,
yeah, of course, but
yeah, I mean, that's all you're looking to do is you just have 2 different endpoints. You want to kind of split up your load and run different functions on different endpoints. Then just grabbing the results and passing them through would work fine.
So in one of your slides that was titled Peek Under the Hood, you show various components, including a RabbitMQ server and the consumer. I was curious how tightly coupled those components are. In other words, is it possible for any arbitrary process to consume tasks from that queue?
So if you're within your network that you're running your endpoint, there's possible. I mean, we know of a few different possible ways that different things can happen where another endpoint that someone else is running in a protected space could potentially consume there. But no, I mean, like for example, this is you're actually subscribing to that queue, which is on the internet. No, I mean, you're going to be protected. This is you're sending specific credentials for that user, which then creates a specific endpoint task queue, and so it's really tied down to the user and the specific queues. No. So
thank you.
Yeah.
Great.
Else?
Good. See anybody on Zoom? So great. Thank you.
Okay, cool. Thank you.